Hi, and welcome to part 4 of my Transport to Exam 3 videos. In this portion of the exam, we will be going through and using what we found in part 1s, 2, and 3. Part 1 we found the Lewis relation, in part 2 we found relative humidity between wet and dry bulbs, and in part 3 we found the relationship between the adiabatic saturation temperature and the wet bulb temperature. So in this part of the exam, we will be going on to something a little different, where we will be looking at a cooling tower here that has airflow going in and up it, and hot water going in at a liquid flow rate of L, down through the packing material of the specific area A, and down through to a point that's cold water at the bottom of it, and the Z goes down into negative in the lower direction, which is going to end up causing it to be negative when we start developing our equations. And so what we really want to do is that this whole part of the exam is that we are going to be looking at trying to find the rate of change of the mole fraction of water with respect to the change in distance of the distillation column of the cooling tower, the rate of change of the temperature of the water as it goes down the cooling tower, and the rate of change of the temperature of the gas as it goes up the cooling tower. And so just looking off this at first glance, we can tell that because we have our Z going down in the negative direction, but it's also going down with the direction of the water, that is going to be inverse more than likely than what we're going to see with the rate of change of gas temperature, because that's going to be going up the cooling tower while this is going down. And so the first part that we're going to want to look at is that we're probably going to want to start with the rate of change of the mole fraction of water with respect to the change in distance with the cooling tower. And first thing that we will know is that because it is liquid flowing in and cooling down, gas going up, we will be losing some energy and some sort of mass of this water to evaporation and heat change. And so we will have to go ahead and find that out with the total molar gas flux. So this is going to be equal to the gas rate of air and the gas rate of water that's in the vapor phase. And so this will be important in just summarizing the whole the total characteristic of the cooling tower and what we're trying to get here. And so now we have this, we can start looking at the aspect of, since we are looking at this one first, the rate of change of mole fraction of water with respect to change and distance, we can go ahead and look at this in terms of a mass balance, because everything that should be coming out here should be equivalent to what's leaving, despite losing probably some sort of mass along the way due to change in energy or change in other aspects, heating, other ways around that. And so we can start by developing this mass balance equation where we have the cross-sectional area. Here, slide out to the way a little bit. So we have this cross-sectional area. This is going to be multiplied by the rate and change of this total gas flow rate that we have right here, all divided by the molecular weight of water multiplied by the mole fraction of water here. So this will be the inlet of what we have pretty much going down into it. And this is going to be equivalent to the negative, and this is where this, I was speaking of it earlier a little bit, where this will be negative, and this is just because it's going down in the aspect of the y-axis. So the Z is going down, so this is why the main reason why we have this as being negative, because we kind of have to keep it as that way. And so it's going to be negative Kc, which is the mass transfer coefficient, multiplied by the difference in the concentrations between the surface and some point far away, also multiplied by cross-sectional area and the specific area, which is a area per volume basis. Whenever we see this A times big A, it's going to be an area per volume basis with respect to the volume of the cube compared to the area taken up by the packaging pallets. And this is going to be multiplied by the change in dz. And so now we have this equation set up, it's actually going to be pretty easy on what we need to do from here on the rest of the way. We can see that these A's cancel out right away, and so that'll leave us with the differential change of the mass, the airflow rate over the molecular weight multiplied by the mole fraction, multiplied by what we have left over here. But what we can do is that we can actually take out this this component right here, because it's going to be roughly a constant value. And so this will actually be nice because we can take this out and we can actually divide this over on this side, and that will end up leaving us with dy over here. We could just simply divide dz back over on that side, and that'll give us our dy dz value on what we wanted to look for the rate of change of the mole fraction with respect to the change in area. So say we did pull this out, we would then be left with dy, and we would divide over dz. And, oh, sorry, something just fell over there. Where's that at? Yeah, so we'll take this out and we'll divide this all over here. And so it's going to be negative kc multiplied by the change in the concentration at the surface and the concentration someplace else multiplied by the specific area. And then this will be, so keep, change, flip. So I think some molecular weight will be up top here, and total gas flow rate's on the bottom. So I'm pretty sure that looks correct for the time being, but we can even actually modify this even more, and that's what I was looking at trying to do. And so we can actually go ahead and modify these concentrations to represent the partial pressures rather instead, and make it look at the aspect of being an ideal gas. So we would end up taking out this and this, the negative mass transfer coefficient and the specific area. And here, I'll just go ahead and erase this, because I'm going to be needing the space to go through the other two differentials here in a second. And so pretty much what we will do is that we will transfer that molecular weight over the gas flow rate multiplied by these concentrations, and that's going to give us the partial pressure of a ideal gas. And so we can pretty much do that, and I'm just going to rewrite it here to save some space. Negative mass transfer coefficient and the specific area A are going to get pulled out. That's going to leave us with the partial pressure of saturated partial pressure of water at temperature water over the rate constant of gas multiplied by the temperature of gas. And then this is going to be subtracted by what is going to be the mole fraction of water in that cooling tower at that moment. And this is going to be multiplied by the total pressure all over the same gas constant times the temperature. And this is pretty much what is going to have you left with your dy dz value. And so pretty much a better way to also to set this up, just so we have better reference for it in the future, and that's going to be pretty much setting up a new variable for this half of the equation. And so we are going to pretty much reset up and reevaluate this equation so that we can have this set up. And so we're going to have this negative, or this mole flux, this NW, is going to be equal to exactly what's inside of this equation multiplied by the mass transfer coefficient on the outside. And so that's going to end up happening, just being a lot easier. So this will be Kc multiplied. I'm just going to take this right here, just draw a little arrow, just to once again save space. And so that's going to be our new value. So in actuality, our dy dz is equal to A multiplied by the molar flux of water at this point. And then that's going to be, just 1 second, I'm going to get a drink of water. Okay. Sorry, I was also just picking up what fell. So, this is actually be this molecular weight times the gas flow rate that we had up here, all over the molecular weight of water, multiplied by the flow of water. And so that's going to be our first equation that we have for differentials that we're going to be solving for. And this represents the rate of change of the mole fraction of water with respect to the rate of change of the area of this going down the cooling tower. And we will actually end up using this later when we end up solving for our second and third differential equations as well. And I'm actually going to go ahead and just clear all this up just to have a little more space again, because I know the other two are going to take up a little more than that one did. That was probably the easiest of the three, but I'm just going to rewrite this up here. It's equal to specific area times gas flow rate over the molecular weight of water is equal to multiplied by the total molar flux of water. And that's going to be number 1. So now we can actually go into the second one we want to look at, and that's going to be the rate of change of the temperature of water with respect to the same area. And when we're going to do this, we want to actually take into effect and look into this little area DZ, this rate of transfer through that area. And that's mostly because when we're dealing with these temperature changes with respect to area and respect to the change in distance and where we are at the point in the cooling tower, we have to look at it more from an energy conservation standpoint to find out how much energy is being lost and gained in between this area. And so we're going to have to actually set up energy energy balance equation from enthalpy in and enthalpy out once again, similar to what we kind of did with I think it was number 3, probably part 3 of the equation or the exam. So it's going to be very similar to that, where we're going to have to set up enthalpy in and enthalpy out. And so enthalpy in, so I'm going to write on here enthalpy in, enthalpy out. And so enthalpy in on this side is going to be equal to that cross-sectional area multiplied by the liquid flow rate, which we haven't really brought in, but it's up here, this hot liquid flow rate when it's going in. That's going to be our liquid flow rate that we're using for this equation, multiplied by the heat capacity of the liquid phase being used, which in this place is water. That's going to be a pretty easy one to use. And then this is multiplied by the rate of change of the temperature of water. And so that's going to be our enthalpy in, and we're going to be setting that equal to our enthalpy out, setting up the and finishing the energy balance equation. And this one's going to be a little longer just because of the fact on the enthalpy outside we have to account for the rate of change of rate evaporating of water that's being lost in that heat, in that transfer of energy, because it's going to be losing energy and cooling down. So it's part of that's going to be evaporating into the vapor phase and going into the gas that's in the air that's being transferred in that as well. And so that's why we're going to have an extra unit on the back side, and I'll outline that on this here as well. So anyway, this one's going to be very similar at the start, where we have this specific area multiplied by the cross-sectional area, which is giving us a area by volume basis. I mentioned this up here when we were solving 1. So anything little a multiplied by big A is area per volume distance, or area by volume basis. We also have to bring in our heat transfer coefficient here, which is going to be H. And this is going to be multiplied by the rate of change, or the difference in the gas phase and the water phase of the temperatures. And then this is going to be all with respect to the change in excuse me, the rate of change with respect to the area where we're at in the cooling tower. But this is all going to be subtracted by that energy that's being lost by the evaporation of water as well. And so when we do that, we're going to have to subtract the heat of vaporization multiplied by the molar flux of water. And this is going to be multiplied by the cross-sectional area again. So this is going to end up actually allowing us to cancel out the cross-sectional area across any point on this, which is going to be pretty nice, and it's going to help us clean up. It's also going to be multiplied by the specific area, giving us a volume, area by volume basis again, and also with respect to the rate of change of the cooling tower that's happening. And so now that we have this equated, it looks pretty well involved for the most part, I would say. At least lets us definitely look and see how we can easily pretty much affect this and change it. So like I said, these A's will cancel out, so we don't have to worry about that either. And that'll leave us with the liquid flow rate multiplied by the heat capacity of the liquid phase multiplied by the rate of change of the water. And so what we could actually do and make this a little more easier is we can also divide over dz and divide over L, or the liquid flow rate multiplied by the heat capacity of the liquid. And this will actually give us probably our I think our final equation of the rate of change of the temperature of water divided by over the rate of change of the distance that's being traveled over the cooling pipe. And so what we can do there is we will have take out, so we'll be left with temperature of water divided by temperature, change over that, this will be equal to, we can pull out A and out front. I need to make that into the numerator. So A can be brought out, multiplied by H, temperature change between gas and water, all minus heat of vaporization times the molar flux. And this is all over liquid flow rate multiplied by the heat capacity of liquid phase. And so this describes this describes the temperature change of water that is taking place in the cooling tower with respect to it traveling through this area designated DZ. And so that's going to make sense, just because it's going to be cooling off, it's going to be losing that temperature. And so having the subtracting off this heat of vaporization multiplied by the flow rate, or the molar flow rate of the liquid, makes sense. So it's because it's going to be losing some sort of energy as it evaporates off. And that is actually going to solve it for the second differential equation we are going to need for this. So now we have one more differential equation we need to solve, and that is going to be for the rate of change of the gas phase with respect to where we're traveling in the cooling tower rather than the temperature of the water phase. And so the way that we're going to start this off is going to be pretty similar to how we did number 2, but the main thing that we're going to be looking at and how we are going to analyzing this is that we know it's a steady state because there weren't any rates given to us, but we are going to have to really, I guess I'll need to say this first before we actually go into that next part. So the rate of change actually, because we know it is a steady state flow with any of this, the enthalpy of water minus the enthalpy of the gas is going to have to be equal to 0 because it is a steady state change. So this actually ends up telling us that the rate of change of the enthalpy of water is going to be equal to the rate of change of the enthalpy of the gas that's being passed through that. So that's actually going to be very important for us setting it up, because we have to look at the change in enthalpy of the gas and equating that to the change in enthalpy of the water to give us our two input and output equations. And so we're going to have to start with the enthalpy of the gas that we're going to have to find. And so I'm trying to think of the best way to write it. This is still in the shot. So this is going to be actually equal to the rate of change. And once again, I'm just pretty much expanding these two equations so that we can set them equated to each other. And this will then allow us to solve for this differential right here, the differential of the temperature of the gas over the differential of the rate of change of where we'll be moving inside of this. And so this is going to be multiplied by the cross-sectional area multiplied by the gas flow rate here, also multiplied by the heat capacity of the gas and the temperature of the gas that'll be flowing in. And so this will be the first part of that, the first units of this equation, but there's also going to be a second part because similar to how we have to take into account the evaporation of water into the water phase of the gas lines, we're going to have to do that same exact thing for this side, but instead of it being subtracted off like we did with the water, it's actually going to be added on. So this is going to be all adding on to another unit, inverse of pretty much of this right here, where it's going to be the heat of vaporization multiplied by the gas flow rate constant that was also used over here. And we're pretty much alternating that out for the molar flux of water that we used up here. So it's pretty much the same thing, just kind of inversed. This is going to be also multiplied by the mole fraction of water, the cross-sectional area of A, and it's going to be all divided by the molecular weight average that we have. And so this is actually your first differential that you're going to be using, but it's pretty rough around the outside, if I'm going to be honest. We haven't been able to, and I said it equated to the outlet, the outlet enthalpy of the water, and that's actually really easy because it's given to us right here. So this is going to be so it's going to be the cross-sectional area, specific area of A, multiplied by the heat transfer coefficient And this is going to be all multiplied by this temperature change between the gas and the water. And also we have to take into account, once again, this second set of coefficients and variables here, which is again taking into account that evaporation of the water into the liquid gas phase. And so we are going to still have to add on this heat of vaporization multiplied by the molar flux multiplied by the specific area and the cross-sectional area. And so that's going to end up being equated to our outside. I also forgot the DZ. There should be a DZ on this one too. Okay, so now we actually have that all set up, I believe. Yeah, okay, that looks good. So we have this all set up, and this is going to be the equated energy balance for the rate of change of the enthalpy of water and the rate of enthalpy change of air being used in here. And so what we got to do now is that we are going to pretty much, first off, we can cancel out the A's. We'll take out the obvious thing. So we're going to cancel out all these A's for all the units over here, because we're going to divide that A over here, take out those ones. That'll work out. Next thing that we can do is that we can do a couple of things. So what I think I'm going to do first, so I'm going to take out all the constants in here so we can get this rate of change of dG left by itself. And so this will be brought down into over here, where we have the gas rate constant multiplied by the heat capacity of the gas. It's going to be awkward to write. I hope it's within the shot too. If not, I'll just raise it up. But so we have those two constants brought out, and that'll leave us with the rate of change of Tg over dz, which I'm just going to divide over dz in this step as well. And so pretty much doing the same thing over here, where we have this. We can take out this, the heat of vaporization, the gas flow rate, and the molecular weight average. So lambda, that, and the molecular weight average. And this is actually going to leave us with another differential, but we solved this earlier, which is dy dz, which we're going to end up having to substitute that in to give us our final equation that we're going to be using. And so, but before we actually do that, we still need to equate over this right side of the equation, which is going to be equal to specific area multiplied by heat capacity multiplied by the rate differential in the temperatures between the gas and the water minus the multiplication of the heat evaporation of heat constant multiplied by the molar flux of water multiplied by the specific area again. And so now this is that more it's a lot prettier than what we have up here, to be honest, because we have this TGDZ, which is what we desire to get for our last differential, but we also have this dydz that's included right here. And so when we actually include that dydz, we are going to end up having to cancel out a lot of the values that we currently have standing here. And so we will be left with a plug this in, we'll have an nw over dy multiplied by lambda. And so this is going to end up actually canceling out this whole unit when we plug this dy dz in up here, up and down into here. So that whole thing is going to be pretty much gone. And it's also going to be taking out these variables as well. And so we're actually left with this what's actually very pretty, this gas flow rate constant multiplied by this heat capacity of gas multiplied by the rate of change of the temperature of gas over the rate of change of traveling through the cooling tower. And this is going to be equivalent to the specific area multiplied by the heat transfer constant multiplied by the differential and the difference in the gas and temperature of the water. So this is actually going to give us our final one here, which is the rate of change of that gas, temperature of the gas, with respect to the air, where they're at in the cooling tower, multiplied by this value that's left on this side, the specific area multiplied by the heat capacity, heat transfer coefficient, multiplied by the difference in the temperature of the gas phase and the water phase, all divided by the gas flow rate and the specific heat capacity of the gas. That will give us our third differential equation. And we are going to go through and pretty much code and explain these and use them in Python in the next part of this exam to get through and give us some values of what we could potentially be getting to solve the equation if we were getting the scenario for the cooling tower. So thank you, and I'll see you in the next part.